Welcome back to the third part of Lesson 1. In the last part of this lesson, we looked at extruders, both single screw and twin screw, and said that they are the workhorse of the polymer processing industry. What I'd like to do in this part of Lesson 1 is to examine three different processing operations that have extrusion at their core: film casting, film blowing, and injection moulding. These three operations are widely used. For example, the global market for cast films was worth about $75 billion in 2022, the market for blown films about $30 billion, and injection moulding is forecast to be worth $460 billion by the early 2030s. So, let's have a brief look at each of these three technologies, as again throughout the first part of this course I'll be discussing a lot about them. Now, we're talking about extrusion-based operations. So here on the whiteboard is a reminder of what a single screw extruder looks like in diagrammatic form and also in real life. Now, the magic happens downstream of the extruder in all these operations. And so the type of finished product we're thinking about can look like rolls of film for a film casting process, and rolls of film for a film blowing process, and perhaps a finished object, a discrete item, a box, a moulded part for injection moulding. So at this point you might be asking, very reasonably, why are there two processes to make films? Surely doesn't one just do what we want it to do? And the answer is, well, there's actually a great deal of difference between films made by the cast film process and films made by the blown film process. And we're going to explore this in the final part of this lesson. And the motivation there is to illustrate it's not only the polymer that defines what the product can do, it's also the nature of the processing. And so it's really important at the outset of polymer processing to realize that polymer selection is important, but also a lot of material properties are imbued to the product as a result of the process. But more about that in the final part of this lesson. So we've got these three different products. We've got cast film, we've got blown film, and we've got injection molded items. So let's start by looking at the cast film process and talk very briefly through the various components of it. And you'll be examining this in a lot more detail in the second part of this course. So, life starts with the extruder. There we have diagrammatically on the whiteboard our single screw extruder with, say, a pelletized polymer feed. Then we have our shape forming part, the die, the film casting die. Now, what we're trying to do with this die is to convert a flow of polymer coming through the extrusion barrel, which might be, I don't know, a few inches internal diameter, into a great big wide flat sheet. And so the flow path in a film casting die has to be incredibly carefully designed. I've put a picture of a film casting die on the board there, just to give you a feel for relative dimensions. These dies can be 1 metre or more wide, because the sheets we want to extrude might be 1 metre or more wide. They are also typically producing a fairly thin product, so the exit orifice from a film casting die might be 1 metre or more wide by maybe 6 or 7 or 8 millimetres deep. So imagine for a moment trying to design a die to give you equal pressure drop across the entire length of that die, because one doesn't want more flow to come out of the middle of the die than at the ends of the die. But again, die design will be talked about a lot more in the second part of this course. At the moment, all I want to do is to give you a teaser to make you think, oh, that's actually quite a tricky problem, because it's well worth knowing how to solve that problem, and that's what the second part of this course is going to teach you. So you've got your extruder, you've got your film casting die. Out of your film casting die will come your molten sheet of material. What we then want to do is to solidify it, and so as close as we can physically get to the die, we put a chill roller. That molten web of film contacts the chill roller, and the chill roller will be rolling at a speed that is slightly faster than the materials coming out of the die, and so in the melt state it's drawn extensionally, and so the material will become longer and thinner. And the thinner the material is, the faster it will cool, because in this case conduction is going to be the limiting means of heat transfer, and the thinner the film, the faster the conduction will happen through the thickness of the film. So once the material comes off the chill roller, it will be solidified. What happens then, sometimes optionally, sometimes not, is the material passes to a second roller, which will be going at a higher rotational speed compared to the chill roller. And in between these two, the material will accelerate and will be drawn in its solid state. So we call this cold drawing. And the reasons for this is it changes the orientation of the polymer molecules. And we're going to talk a lot more about this and why that's a good thing to do in the last part of this lesson. So you've got your chill roller, you've got your stretch roller, and then you've got some downstream machinery of that then might, for example, spool the film up onto a cardboard roll such that you can disengage that roll, put another roll in, and again roll the product up. And there's typically lots of rollers and tensioning devices required to do that. So that, in very, very basic sketch form, is a schematic diagram of a simple cast film line. You've got your extruder, you've got your die, you've got your chill roller, you've got your stretch roller, and then you've got downstream equipment that helps to handle the finished product and spool it onto cardboard tubes. So let's have a look at its close brethren, film blowing. I love film blowing processes. I think they are absolutely fantastic because if you go into a film blowing factory, it's an incredibly visceral experience because these devices are big. So again, it starts with an extruder, very much the same as you do with film casting. You might be using a pelletized polymer, for example, polypropylene or ethylene vinyl alcohol, something of that nature. And of course, the shape forming part is very much a clever piece of design, and that's your film blowing die. Now, your film blowing die is incredibly different to your cast film die because, first of all, what you're extruding here is basically a thin-walled tube. Let me show you a picture of a film blowing die. We can see that it's cylindrically symmetric. We can see there's a whacking great hole in the middle of this die, and that is not where the polymer comes out of. The polymer actually comes out of a very, very thin annulus a good diameter away from that hole. What comes through that hole is air, and the purpose of that air is to blow a great big bubble. Why are we doing this? Well, if you think about what's happening, it's a little bit like blowing up a party balloon. You get a massive amount of circumferential stretch. The diameter of the party balloon will increase massively as you blow it. Likewise, the diameter of your polymer bubble will increase massively in diameter under the internal pressure of the air inside it as you apply that air. And that circumferential stretch gives us some very good properties. Again, we'll be talking about that in the second and final part of this lesson. So you blow this big bubble, and then you try and keep this big bubble stable, because if it's not stable, it has a tendency to wave around and generally do things that are not amenable to a good finished product. And so it typically goes up a set of rollers or guides of some sort that keeps that bubble nice and vertical. The bubble is collapsed by a set of rollers at the top, and the distance between die exit and rollers can sometimes be several floors in a factory. These bubbles can be vertically very, very large. Now, much as with cast film, these rollers will be rotating at a speed that is higher than the material is coming out of the die. And so again, we get some drawing of the polymer in the extrusion direction. So this is quite interesting because we're stretching the polymer circumferentially and also axially. Again, we'll be talking about that in the final part of this lesson. Some way up this bubble, there's air blasted onto the outside of this bubble, and we get what's termed the frost line. That's where the material sets. So the very base of the bubble is still molten. That's where that initial inflation takes place and the subsequent thinning of the film. But a little way up, you'll get the film solidification, and this is the frost line. And you can typically see an opacity change on bubbles where you've got your frost line. So downstream of the nip rollers, again, you've got other bits of handling equipment. You might have some slitting equipment, because don't forget we've still extruded a polymer tube here. We might want to produce polymer sheets, so you might slit one edge of the tube to open that tube out to a sheet, or we might keep it as a tube. For example, we might be making plastic bags, and all we need to do is heat seal that cylindrical tube in various places to crimp the two sides of the tube together to form a closed structure, and then stamp out a bag from that. So that, again, in very basic schematic, is a film blowing line. But I can't resist showing you a picture of the bubble because it's worth seeing. It's slightly hard to see in this photograph, but the core components are the air supply, supplied by the flexi tubing in the base of the picture. There I've arrowed it on the board. Then you have your blown film die, vertically oriented. The film here is coming vertically upwards out of the die. Then that film is inflated to produce your bubble, a cylindrical film. And your polymer bubble you can just see there if you look very carefully. It's there inflating out of the die. And then you've got that scaffolding and that blue structure above it to keep the bubble in place vertically above the die, to stop it waving around and to keep everything nice and stable. So that's film blowing. Let's talk about one last polymer processing operation that involves extrusion, which is injection moulding. Very, very different to the last two processes. However, it still has as its heart an extruder. Now, the extruders for injection moulding are quite cunning, because not only can the screw rotate, it can also reciprocate in and out. And we'll see why that's important in a minute. So you've got your hopper feed for your pelletized material, you've got your extrusion screw contained within a barrel, and then you've got a mould. And I've pictured here on the board 1/2 of the mould cavity. And so one can imagine if we get polymer into this cavity, it's going to fill the cavity up. But if we want to make, say, a box, we need another part of cavity there. So moulds come in 2 halves. And I've shown you a photograph on the board of a complex mould. And it's amazing what you can injection mould. You can injection mould really, really, really complex shapes. Backs of mobile phone covers, for example, or gears to put into a power tool, or maybe cartridges to put into an antiviral test for a medical device. You can injection mould very, very complex shapes. And one of the things that we've got to do when we injection mould is not only form the shape, but also get that material out of the moulding line. So what we have as the other part of the mould is something mobile. So we've got a moving platen. And so let me show you the sequence of operations that happens to injection mould, for example, a simple box. Our mould, which I've shown in cross section, will define the outside bit of the box. The platen will define the inside bit of the box. And so the platen will move over into the mould cavity, like so. The extrusion will be working. But what happens is the extruder screw reciprocates forward and pushes molten polymer into the cavity that's defined by the union of the platen and the cavity. The horizontal white lines there are vents, because evidently we're pushing material in, something's got to leave, air, gas, and typically a little bit of flashover as well from the die, a bit of polymer that leaves the mould cavity. So there we have something moulded in the cavity now, but we need to get the material out, so the platen moves back, and then hopefully, all being well, the injection moulded part can be easily released from the die. So you can imagine there's all sorts of fun and games here involved in designing a mould in a cavity from which you can successfully detach the finished object. And so you hear talked about mould release agents, or dies or cavities specifically designed for mould release, and that can involve various coatings. So that is the basics of injection moulding. So let's briefly summarize a few key points. We've seen 3 major examples of extruders used in polymer processing. We've seen 2 processes that look quite similar. We've got film casting and film blowing. They both produce very thin, flat films. I've also shown you an example of injection moulding, which can produce some incredibly complex shapes for all sorts of engineering, consumer, medical applications. Effectively, if you can design a mould for something, you can injection mould it carefully. We'll be talking a little bit more about blown films and cast films in the final part of this lesson. And I want to do this to reinforce that really important point I made at the beginning of this part of the lesson, which is that the properties of the final product are as much a product of the processing as they are of the polymer. But I'll leave that until the final part.